Okay, so thanks and welcome everybody. So this is a tutorial on lifting, which is this super exciting technique to prove communication lower bounds. And the way I planned this is that the first half would be, I just want to gather as much simple observations about these tools, so nothing difficult. I want everybody to try to follow. But then when I've lulled you into a false sense of security, next half, bang, I actually want to prove a proper lifting theorem. So it'll be a bit more substantial, but we'll go very slow. Also, I think I see many lifting experts in the audience. I wonder what they're going to get out of an introductory tutorial in this. But maybe they want to hear their names mentioned throughout the talk. So I can provide that. So I hope that if you're familiar with theoretical computer science, you have heard about decision trees and communication protocols. So I'll still kind of quickly recall them through pictures. So this tutorial is all about relating these two communication or computational models in interesting, non-trivial ways. So let me recall decision trees. There may be the most simplest computational model you can imagine to evaluate a Boolean function. So here you would fix your favorite Boolean function on n input bits, and you could ask, what is its query complexity? What is the shallowest decision tree computing it? So a decision tree is just a tree whose nodes are labeled with input variables, and you evaluate it by starting at the top. It's labeled by some variable. That means you go to the input, you query that variable, you branch two ways depending on the value of the variable. And so you trace a path down the tree until at the leaf you output a value. So any Boolean function on n input bits can be computed by such a thing, at least if you allow height n. You read all of the input bits. But some Boolean functions you can compute much more concisely with shallow decision trees. I guess for notation, when I talk about this world of decision trees or query complexity, I tend to like to denote the input by z, just to reserve x and y for communication complexity. So again, I hope you've heard about communication protocols before. You have Alice and Bob. They've been given some inputs, x and y, and they're supposed to communicate with one another, so send messages back and forth, trying to compute the value of some function, capital F. So again, you could imagine fixing your favorite such function, whose input comes in two parts. And the two players, they just want to minimize the overall number of bits that are communicated. Well, you can also view communication protocols as trees. So I've drawn here what a protocol looks like as a tree. So a protocol could start with Alice sending a bit. So Alice, her bit is simply an arbitrary function of her input x. So this is what it means. You evaluate an arbitrary predicate of Alice's part of the input. So that's one bit of message. So the protocol, in some sense, branches two ways, depending on what the first message sent was. Then Bob speaks. Bob sends the next bit. It's an arbitrary function of his input and the messages so far. So if Alice sent a 0, now Bob applies some predicate to his function, depending on the 0 that was sent, and otherwise an arbitrary predicate of y. In the end, you end up at a leaf. That means the protocol outputs a bit. And it should be perfectly clear that communication protocols viewed this way, they're much more powerful than decision trees. So in a decision tree, again, you branch on the values of individual bits in the input. But in a communication protocol, you can branch on arbitrary predicates of either the Alice part of the input or the Bob part of the input. So if I have a Boolean function that admits a shallow decision tree, then immediately you get a communication protocol for this function. Okay, every query to a bit is just replaced by the player who owns that bit communicating its value to the other player. And of course, it also should be relatively clear that not only are communication protocols at least as powerful, but they really can be a lot more powerful. So let me just begin with a very silly example to demonstrate this. So just consider the n-bit OR function. So I claim that it's really hard for decision trees. So here's my notation. I write D for kind of deterministic complexity, or deterministic decision tree complexity of the OR function on n bits. So I claim this is just n. Any decision tree computing the OR function needs to read all of the input bits. And the way you would argue things like this is normally you design an adversary strategy. You're trying to show this decision tree that hypothetically computes OR must have large depth. So you begin thinking as an adversary. The decision tree makes a query somewhere, and you as an adversary get to decide the query response. What is the value of this bit? So imagine a decision tree initially doesn't know any of the bits, queries something. We as an adversary can always answer 0. So you keep querying bits, you just get answers 0, 0, 0. You still don't know whether the OR function evaluates to 1 or 0. So you can prolong fixing the value of the OR function this way. And really, you have to query all the bits until you're sure. OK, so that's easy. But also, the communication complexity of the OR function is a constant. So the deterministic communication complexity of OR. And no matter how I partition the n input bits amongst the two players, well, this is something like 2. Like Alice looks at her bits. Is there a 1 in my input? Yes or no? Bob does the same check. And that's basically 2 bits of communication. So the whole point of this research agenda for lifting is to try to find situations where this doesn't happen, but rather the two models, they're very different, but we'd like to find general situations in which you could equate the powers of the two models. So situations where to analyze communication protocols, which is pretty difficult actually, you could only analyze these simple things, decision trees. So that's the really high-level idea of lifting, is trying to reduce the analysis of communication protocols to that of decision trees. And there's a really general conjecture of when this equivalence should happen. It clearly doesn't happen for the OR function, but the large class of Boolean functions we conjecture this to happen to is so-called composed functions. So let me introduce these. Okay, and I'll do it again through an example. So maybe the most important, not maybe, definitely the most important composed function is something called set intersection, or sometimes called set disjointness. I think I'll use these two words interchangeably. So this is a communication problem that you obtain from the OR function by composing it with an AND gate. So it's this function. You have the n-bit OR function at the top, and each of the n input bits I replace with an AND gate with 2 input bits. So I have x1 and y1 for the first AND gate. And so then there are n of them. And so I view this as a communication problem. I give Alice all the first bits to these AND gates, and Alice gets all the second bits. So what's happened here is we took the OR function and we kind of replaced each of the input bits by this gate that replaced the bit with it shared it with the two players. So at the start of a protocol, if Alice just sees the first bits to these AND gates, she can't really figure out exactly what the outputs of these gates are that are then fed to the, I call it the outer function now, OR. And now it's a theorem that this is maximally hard for communication protocols. So certainly deterministic, but even randomized communication protocols. So it's a theorem, a very famous theorem, that the deterministic or even randomized communication complexity of this set intersection function is, well, the same as the, okay, I should say up to constant factors. The same as the decision tree complexity of the OR function, okay, which is just, well, order n. So I suppose the intuition is that the two players in a protocol trying to solve this function, since they don't know what the inputs to the outer function are, before they communicate enough information about the inputs to a particular gate. So this is kind of one example where we, at least in a single example of a function, we can make the two models equally powerful. I should also mention, why do we call this set intersection? Well, you can think of this function as follows. Think of all the x's and y's as indicator vectors of sets. And so then this function is just computing, do these two sets intersect? Is there a coordinate where both the players have a 1? Okay, so I would say, generally speaking, the most important result in communication complexity is this fact, that the set intersection problem is hard. If you ever see applications of communication complexity in these application areas, like online algorithms, streaming, data structures, what have you, chances are a lower bound for these models is proved by a reduction from this result, that set disjointness, set intersection is hard. So I'll feature this function constantly in the talk. It's just so absolutely the most important. And so I want to now conjecture kind of a vast generalization of the set intersection problem being hard. That this phenomena is just not restricted to this one example, but it's more prevalent. So I call it it's the main lifting conjecture, GASP. I want to just say that the intuition why this function is hard holds more generally. No matter what the outer function here is, and even no matter exactly what type of communication and query complexity I consider, whether it's deterministic, randomized, non-deterministic, what have you, as long as you choose this gate, and we also call it a gadget, if you just choose a small enough, carefully chosen function here, then query and communication complexity should be kind of.
Let me interrupt for just a second. Would anybody prefer that we have a microphone?
Oh, gosh.
Yes. In that case.
Hmm.
Fasten this on up there someplace.
Okay, how about now? Testing.
Say it again.
Do you hear anything? Okay, I start to hear it.
Is that a good
Okay.
level?
Okay, thanks. Okay, just in time for the big bold conjecture. So I want to say that for any outer function, anything you can put at the top, And now I speak a bit abstractly. Pick any type of computation. I just use M as a placeholder. So think of this as some type of computation or model of computation. If you look at its communication version, and you measure the, or you're interested in the communication complexity of this function composed with some gadget. So this would be, you get to choose a moderately sized function that takes inputs from both players, spits out one bit, so it's a generalization of the AND function. So gadget is just a name for this function I plug at the bottom. So then this should roughly be the same as its analogous decision tree complexity. Well, the decision tree complexity of the outer function. Because again, the two players, they don't really know what the outputs of these gadgets are until they spend maybe constantly many bits per gadget to figure out the inputs to the actual outer function. So, I mean, this is, it's not even perfectly formal. I don't know what I exactly mean by a model, but you should think of, again, as maybe a deterministic model. You can define deterministic decision trees and protocols, like we've been discussing, or maybe randomized. So I want to list some results in this way that are known. Actually, there's a huge list. I can only mention a few, maybe the most kind of the simplest ones to state. Okay, so it's a table. Now, what can you instantiate here for the model? And what is the gadget we require? I should say, a statement like this is easily false if you choose your gadget in a bad way. So even the AND gadget, it's not enough for such a general statement. So what if I use the AND gadget and I choose as my outer function just the AND function? Okay, so this would be, so of course, AND composed with AND is just a large AND, and we're back in this situation. So in order to hope for such a general statement, you have to allow a slightly more complicated gate or gadget at the bottom. So I think the most obvious instantiation of this is for deterministic query and communication complexity. And so such a theorem is known when you choose as G something called the index gadget. Okay, so this is a result of Ras and McKenzie from '99. And it's maybe the first ever proper lifting theorem that was proved. Although, it was buried a little bit, and it's only kind of resurfaced recently. But yeah, let me carefully define what this index gadget is. It will be really important in this talk. So I'll just define it here. So this is the index gadget on m bits. So here I give Alice a pointer, so there's a number between 1 and m. So this is my notation for the set of numbers from 1 up to m. And Bob is just holding an m-bit string. And so Alice is given an x, Bob is given a y. The index gadget evaluates just the xth bit of y. So Alice's pointer is pointing into Bob's string, picking out one value. So yeah, in some sense, this is the mother of all gadgets. Normally, when I say index, I mean m here should be thought of as polynomial in the input length n for this outer function. So let's say something like n is 100. So here, under this, these parameters, the gadget is rather small. So Alice would be holding a log n bit pointer, but yes, it's true, Bob has a very, very long string. Nevertheless, to evaluate indexing, the clever thing is, of course, for Alice to communicate her small input, and that takes only log n many bits. So even though the gadget inputs are really large, I think of the gadget as small because it is such an efficient communication protocol. So I suppose to be a bit more careful here, I could conjecture or add to this conjecture a factor which is like times, okay, I don't write it down, but times the communication complexity of the gadget. That would be maybe more precise way of stating it. But we'll always look at small gadgets, so I hope it's not so important. So there's loads of subsequent work to this. The best result in terms of, I should mention, the gadget is the only free parameter in such a theorem, so you would naturally want to optimize it, and it's important to get as small as a gadget as possible. So there is some subsequent work that does prove such a theorem also for the inner product gadget. So this, okay, I need to look up. So two works that have done it independently. So there's Chadabadia, Kochki, Lof, and Mukhopadhyay. And independently by Wu, Yao, and Yuan. So this was a couple of years ago. And so they shrunk the size of the gadget a little bit. So this was log n for Alice, polynomial for Bob. But now inner product we think of as log n for both players. So let me define this function quickly. So this is inner product on b bits. You should think of b as log n. Okay, so both players have a b-bit string, and you're just computing their inner product as Boolean vectors, their inner product over the integers. Okay, so far this is just a natural number, but we take it mod 2, so it's a Boolean function now. So inner product, actually, again, very important function in communication complexity, is an example of a function that's really hard for communication protocols in a really strong sense. So that's a slight improvement, but it's still open to get the gadget size down to a constant, which is the golden standard here. So I'll have much more to say about constant size gadgets in a moment. But let me mention other types of theorems that are approved. So given that a deterministic lifting theorem exists, maybe the most natural follow-up question is to ask it for randomized models. And so this was proven only recently. So for randomized models, I should say, I mean here two-sided error, bounded error protocols. So to define a randomized protocol and a randomized decision tree quickly, think of them as just probability distributions over deterministic decision trees or protocols. And then on any input, if you pick a decision tree at random from the distribution, then that decision tree computes your input correctly with high probability. It's the usual like BPP type of definition. So we now do have lifting for, in the randomized case, for the index gadget. So this is work by me and so Vitasi, Watson. And here too, just recently actually, you can get the gadget size down to log n for both players. This is actually, I was curious, I just looked up recently the paper this should have appeared in at ICALP. It's on the accepted papers list, but not on the program. So I don't know what's going on. But anyway, this extension is due to Chattopadhyay, Filmus, so it's like Coron, Meyer, and Pitassi. Okay. Possibly at ICALP last week. But again, we lack the golden standard, which is a constant size gadget here. Okay, and I should also quickly mention one. So I would say for applications, randomized lower bounds are the most important. So most of our efficient algorithms are randomized. So if you want to prove lower bounds, well, you normally make connections to randomized protocols. But there are more exotic models of communication, like non-deterministic ones. Yeah, I won't define exactly what those are yet, but it's also known that you can do lifting for them. So I view all of these as natural communication models. But there's this kind of, I would maybe say, parallel line of work that does lifting for more linear algebraic complexity measures of Boolean matrices. So a high-level comment is I view communication complexity as the study of the complexity of representing Boolean matrices. So an F whose input comes in two parts you can view as a Boolean matrix, a really large one, where rows are indexed by Alice's input, columns by Bob's input. And so you could ask, what is the rank of such a large Boolean matrix? And for these complexity measures, we also have lifting theorems. But they're kind of slightly different in nature from, I would call these combinatorial ones. These are more linear algebraic ones. So in that sense, the rank of a Boolean matrix is kind of a communication complexity measure. So rank over reals in particular. And you can, to be really precise, to fit into this mold, maybe I'll say log of rank. Just to get the scales right. And you can lift to log of rank from the degree of a Boolean function. So that's when you take a Boolean function, you write it as a multilinear polynomial over the reals, and you look at what's the least degree of a polynomial I can do this with. So interestingly, this is the only case where we achieve the fantastic golden standard of a constant size gadget. And this is work from roughly a decade ago. So Sherstov's been doing this a lot, analyzing these linear algebraic complexity measures, but independently also done by Xi and Zhu. And so there are loads more. Let me maybe mention one more, just because of the connection to applications. There's something called non-negative rank. Okay, so if rank of a matrix is asking how many rank 1 matrices do you have to sum up to represent the matrix, then the non-negative rank of a non-negative matrix asks how many rank 1 non-negative matrices do I need to add up together to represent my matrix. And okay, so this appears in several different contexts, but why it's important here is there are connections to understanding the sizes of linear programming formulations. So this has been trending in the last, let's say, 7 years, is through analyzing non-negative rank, you can actually show lower bounds on the application is to the size of linear programming formulations. And so this is pretty neat. Okay, this measure we lift from is somehow the query complexity analog of non-negative rank. Okay, so it's some, call it conical Hunter degree, but let's not go in too deeply in there. So some of the really neat results from roughly 7 years ago is we can now show that for some NP-hard combinatorial optimization problems, like the traveling salesperson problem, you just can't write down a polynomial-sized linear program to solve traveling salesperson. That result has been like a best paper at Stock or Fox, and it's kind of caused this a bit of a resurgence in the study of this. So you can, using these tools, you can prove these consequences of P not equal NP, which is pretty neat. So there's also, you can ask, okay, we can do LPs, can we do SDPs, like the size of semi-definite programming formulations. And there are also lifting theorems to prove lower bounds there. But okay, so that was a kind of a laundry list. And I also only mentioned really few results. So you could push this a lot further. Even here, you could ask, okay, so you got a deterministic lifting, but you can be more fine-grained. And maybe you want lifting that preserves not just the height of the two trees, but the number of rounds. Okay, that's one goal. Or maybe you could ask for lifting for really small gadgets. People have studied XOR gadgets. XOR is too small of a gadget, like the AND gadget, to exactly hope for such a correspondence. But you can then conjecture another kind of a lifting result. There's work on something called equality gadgets. Okay, Will?
So in the main lifting conjecture, is the quantification on G here, like is it a conjecture is that there exists a constant size G?
Yeah, so I don't want to be, I don't want to go out and make it too formal because it might be false. But constant size, I would so far believe that it should hold for some constant size gadget. But we are not there yet. Which maybe brings me to the biggest open problem. Okay, in short, get these constant size gadgets. Okay, so it's a pointer to this table. It's not really just a single question. You can ask this for any model that has been considered. And there are no formal implications that if you get a constant size gadget in one case, you would get such a thing in another. But you'd hope that the techniques would generalize. And so this is, I call it the biggest open problem. It's the most important because it would have so many implications. So I want to list some of them. Okay, so if you improve these theorems, what would follow? Okay, so these are mostly picked from various application areas of communication complexity. And so firstly, monotone circuit complexity. Okay, so that's a study of circuits with only AND and OR gates, no negation gates. So this goes back all the way back to, well, okay, I don't know how far back, but the biggest results, I suppose, came in the 80s with Rasparov showing that the click function can't have polynomial-sized monotone circuits. Well, these things are still very interesting because there are various connections to other parts of complexity theory. But one result you would get out of the appropriate kind of a constant lifting theorem is optimal lower bounds for this model of computation. So optimal means exponential in the number of input variables on the size of monotone circuits. So current best lower bounds quantitatively are currently exponential in the cube root of n due to Raz and co-authors. Harnik might be the other author. And another consequence of monotone circuits is near optimal separations of monotone NC versus monotone P. So this is a question that asks, can you find these monotone circuits of polynomial size such that the function is computing cannot be efficiently parallelized? So NC, this is class of efficient parallel algorithms. And the first result in this vein was actually the main motivation for Ross and Mackenzie here to prove their first lifting theorem. They wanted an application to separate these two. But you could still ask for optimal separations. So optimal separations would mean a function computed by a monotone polynomial size circuit, yet you need nearly linear depth for any monotone circuit computing this function. So any function you can compute in linear depth by brute force, but you could hope to confirm this in the monotone case. So that's pretty neat. So another application area is proof complexity. And here, well, I mean, there are known connections between monotone circuits and proof complexity. So this is, for some people, not very surprising that you would potentially get applications. One would be, again, optimal lower bounds for some types of proof systems. So I would imagine something like this. Again, an optimal lower bound on the size of refutations of explicit CNF, unsatisfiable CNF formulas in a proof system called cutting planes. So in short, cutting planes is it's a proof system that reasons with linear inequalities. And this has been studied since the 80s. The state of the art here, quantitatively, is kind of matches that of monotone circuits, because the way so far we've been able to prove cutting planes lower bounds is all from deriving them from monotone circuit lower bounds. Of course, you could hope for a more direct proof. And another problem in proof complexity that I want to mention, especially because there are people in the audience who have been doing this, is studying so-called K-clique formulas. So these are formulas that say that for a specific graph, the graph contains a K-clique. Even though the formula really doesn't, but the graph really doesn't contain a K-clique, but the formula states that it does. So it's an unsatisfiable formula. And to refute it, the most naive way is to kind of cycle through all possible K subsets of nodes. And so you would conjecture that in weak enough proof systems, you can't do better. And in particular, for the most basic proof system, which is called resolution. So the lower boundary conjecture is just basically n choose k. And so the most recent work on this is that we do have such lower bounds in restricted cases of resolution, something called regular. So this is by Atserias, Bonacina, Resende, Loria, Nordström, Rasprov. So proof complexity people really care about this. And you would get lower bounds from, well, certainly from constant size gadgets. But for this, you actually only need a logarithmic size gadget. For a lifting theorem, I didn't mention here, but it's another theorem for which we have it for index. But so far, we don't have it for inner product. If you could get it for inner product, this would follow. So then, more applications. I mentioned, this creature rather, on the size of linear programming formulations. Again, the trend here is, you would get optimal lower bounds. So again, strictly exponential in the number of input variables. Then I also have kind of a more meta-theoretic consequence, which is you would get a new proof that this set intersection function really does require linearly many bits, even for randomized protocols. You might be a bit confused, why do I need to prove something that's already known again? But it's absolutely the most important function. And already there are 3 different proofs for this linear lower bound for randomized protocols. Again, the most widely applied result. And the different proofs, the techniques that go into it have been really widely applicable. So I would just like this lifting machinery to kind of subsume or take part in celebrating all the lower bounds you can derive from set disjointness. And so let me now spell out actually why is it the case that if you got randomized lifting for a constant size gadget, why would it give linear lower bounds for set disjointness? It's not quite clear because for a constant size gadget, you can pick your gadget. So maybe you use a gadget G. Doesn't have to be the AND function. And applying this hypothetical lifting theorem for the OR function, you would get maybe a linear lower bound for this kind of a communication problem. Okay, so looks almost like set disjointness, but not quite. I mean, you have this function here, constant size, but maybe it's just random or something. Why lower bounds for objects like this actually do yield such clean lower bounds for such clean functions. So let me spell this out. Why is it the case? And that's, in short, because any gadget you can embed or reduce itself to a set intersection gadget. So if you have your gadget, let's say it's a B-bit gadget. Both players have B bits. B is a constant. Well, I claim that such a function reduces to the index gadget, which is kind of the mother of all gadgets, although on exponentially many more bits. So why is this, actually? So think of any gadget on B bits through this communication matrix, or view it as a matrix. So G is nothing but a Boolean matrix. With 2 to the B rows and columns. Okay, so it's some Boolean matrix. But what's the communication matrix for this indexing function, where M is, right, so M is 2 to the B. So with M 2 to the B, Alice has this number between 1 and 2 to the B. So 2 to the B different rows. And if you think about it, it's a matrix that has all possible columns. So all possible Boolean columns. So index is really 2 to the b rows and all possible, I suppose, 2 to the b Boolean vectors. So it certainly embeds any particular matrix with fewer columns. So was this clear enough? So that's why I call it the mother of all gadgets. If there's a lifting theorem for a constant size gadget, this shows there's actually one for large enough indexing gadget too. So you can kind of, without loss of generality, restrict to the index gadget. But further, I can write the indexing gadget as a set intersection gadget. So I can write it itself as an OR of an in 2 to the b of and. Okay. So I call this set intersection on 2 to the b bits. So why is this? Well, Alice has this pointer to Bob's string. I reinterpret this pointer as just also an indicator vector. So if the pointer assumes m different values, think of it now for this reduction as an m-bit string with a unique one entry in it, in the position that the pointer gives. So Bob has an m-bit string. I don't do anything with Bob's string. It remains as is, but this pointer I transform into this indicator vector. And so now these two strings, they intersect in this chosen position exactly if the corresponding bit for Bob was 1. So, okay, maybe I'll belabor the point if you don't object. So Alice would first have a pointer to Bob's string. Okay, so this is some long m-bit string. And this is just a log, well, an element in here pointing somewhere. But in this reduction, I transform this pointer into, so Alice manipulates her input to also an m-bit string that is all 0, except there's a 1 entry in the mth position. So clearly, these two strings, they intersect just depending on the value in the mth position. Okay, and now I see a nodding of heads. Thank you. So really, this function itself, it reduces through these to the OR of 2 to the b fan-in of ands no. Okay, you collapse these levels. What you have is just set intersection on n times 2 to the b many bits. But b was a constant, so it's still just the set is shown is on like with a constant blow up. Okay, so maybe the take home normally is that, and why we want a small gadget is that for applications like for set intersection, you encounter an exponential blow up in the gadget normally if you want to kind of reduce to clean sorts of problems. So that's neat. Okay, so next I want to prove a kind of a lifting theorem. It's cheating. It's really just more looking at set intersection and what you can derive out of it. But the result might seem pretty impressive at first blush. It's also very easy. So so I call it following theorem, lifting sensitivity. And also I want to kind of, so sensitivity, probably many of you have heard that there's some huge conjecture about sensitivity that was proven recently. So, this is my motivation to kind of catch on to the hype and include a theorem about sensitivity. So I claim that so we're not going to prove some restricted sort of a lifting theorem. And I should credit this to maybe Zhang and Scherster from 2009, although, okay. So I claim there's a constant size gadget such that for every, and now I have to make a concession. Normally when I say an f, I allow even a partial function. So maybe it's not defined on all inputs, but here I expressly require f to be total. So it's defined on all Boolean inputs. And I claim that the deterministic communication complexity of the composed function, actually even randomized, but let's stick with deterministic, is, well, we'd like it to be exactly the deterministic decision tree complexity of f, but I'll just prove this up to polynomial factors. So that's already kind of pretty hopeful. I should say it's again open to actually prove this for a constant size gadget and just a constant factor relationship, no polynomial loss. But Rasen Mackenzie again proved this, but for a larger gadget and no polynomial loss. So I'll prove this, but what I'll actually prove is, to be more explicit about it, that again, so there is a gadget such as all total that I can get a lower bound on the deterministic communication complexity via sensitivity. So okay, so let me quickly define what sensitivity is in case you haven't seen it. Okay, so the way this is defined is I first define sensitivity at an individual point in the Boolean cube. So I just say S. Sensitivity of f at a particular input z is just the number of coordinates that are sensitive, meaning the value of the function changes if I flip the coordinate. So it's the number of coordinates such that f of z is different from f of z, and here's my notation, z with the ith bit flipped. So this is kind of the local sensitivity defined for a single point, but then the sensitivity of the function itself is just the maximum over all inputs of the sensitivity at that point. So it was the sensitivity conjecture. It was open for a long time. The question was whether this quantity was polynomially related to the decision tree complexity of the Boolean function. It was only recently proved. Now, if you assume the proof of this conjecture, it says that, so these two guys are polynomially related. So this was what Hao Huang proved. So there's a poly relationship. So I suppose, assuming that you you're convinced that it suffices to prove just this, the second theorem. You know, for a relationship, the upper bound is always trivial. If you have a decision tree, you get a communication protocol at no loss. But this is saying if you have a, let me phrase this a lower bound. So if the decision tree complexity is high, then at a polynomial loss, the sensitivity is high, and then we prove a lower bound on communication like this. I should mention, this stuff doesn't really rely on the proof of the sensitivity conjecture. You can prove a lower bound also using something called block sensitivity, but let me not do that. Block sensitivity is not what was known for the longest time to be related to decision tree complexity. Okay, so let's prove this, and I claim it's just a reduction from set disjointness. So I start with set disjointness. Not on n bits, but s bits. So s is this sensitivity of my f. And so I know this requires linear communication. I just need to embed, again, reduce, embed this as a submatrix of the communication matrix of the lifted function. And let's pretend, for starters, that, in fact, the sensitivity is maximized at z equals the all zeros vector, just for starters. So suppose this maximizing z is all zeros. And maybe the sensitive coordinates are the s first ones. Okay, so a small remark I have to make about the lower bound for a set intersection. But the lower bound holds even under the following promise, which is that it's called the unique intersection promise. So it's a promise problem where I guarantee either the two sets are completely disjoint, meaning the outputs of the gadgets here are all zeros, or there's at most one intersection, meaning the outputs of the gadgets are a Hamming weight 1 string. Okay, so if I call this output, well, should maybe come up with a new name for it. Okay, let's call this string z prime. So the promise is that z prime has Hamming weight 0 or 1. Okay, and these results, they hold even under this promise. And that's what I'm going to use. Okay, so here's the kind of the target function I want to reduce to. F composed with some gadget, which we haven't picked yet, but let me try to do it with the AND gadget. So what would happen if I put the AND gadget here? Can I then complete the reduction? Okay, so let's say here are the S first gadgets. And if I really am allowed to assume this, I claim the reduction is very simple. So what do you do? I have x1 up to x s and y s. Well, I just take these inputs. So I'm now kind of describing an embedding of this partial matrix inside the communication matrix of this. I take these inputs to my promise set intersection, and I just copy them over here. So x1, y1, xs, ys. Just copy them. And also I need to hard code some bits for these coordinates that are not sensitive. So I've just maybe put in zeros here, which cause the gadgets to also output zeros. So what happened here? I claim that the reduction is complete, at least in this case. So here, it's hard to distinguish between the all zeros gadget output and the Hamming weight 1 output. But what's happening here, when the gadget output all zeros, then I'm feeding all zeros to F. It's one case. Another case was the gadget outputs have Hamming weight 1. Well, similarly here, the outputs have Hamming weight 1. And in particular, the 1 entry is in one of these positions. And so then F changes value. So this function is sensitive, it has 2 different values on the 2 different cases here. So I didn't do much. But okay, we're not quite done because of my weird assumption about the sensitive input being the all ones. But it's not hard to massage this a little bit. So what if I have a general string? So maybe there are 1s somewhere. If I have a 1 in a place that wasn't sensitive, well, in my reduction, maybe I just change these hard-coded values. Okay, I hard-code 1s here. Okay, this is outputting 1. But more interestingly, what if I have 1s amongst the sensitive bits? So maybe the first bit of the sensitive input is a 1. Well, then I would really like to kind of make the reduction work. I would really like to just insert a negation gate here. Okay. So for this function, the reduction still works. I mean, I flipped a bit here, and I just fix it by putting in a negation gate there. So it's as if I really wanted to use a NAND gate in this first coordinate. Well, I mean, we can do that. We can just pick our own gadget any way we like. So at start, we were trying to do it for the gadget that was the AND gadget. Okay, so this is the truth table or the communication matrix for AND. But now we'd also like a NAND gadget to be at our disposal. Well, then let's just use a larger gadget. So now the other player has actually a trit as input. Here's my AND function. Here's my NAND function. So okay. So for this gadget, I'm done. I can embed this picture inside here. So AND gadgets, just coordinate-wise, they embed here. NAND embeds here. Okay, so that's the choice of the gadget we use and the end of the proof. So that wasn't terribly hard, and we kind of already have a lifting theorem with polynomially tight bounds. Of course, much of the usefulness of lifting is actually to get optimal bounds or safe in parameters. So this is not terribly useful, although maybe I'll mention one application of this simple lifting, which is pretty famous. And that's an application to the log rank conjecture. So this used to be, so who has heard about the log rank conjecture? Okay, wow. I'll mention it briefly. Is deterministic communication polynomially related to log rank of the Boolean matrix? So here's an example, or at least a sketch of an example, why if there's a polynomial relationship, well, you can't hope for a linear relationship. This is what this example is showing. So this is due to Kushilevitz, Nissan, and Victorson. And so they separate deterministic communication from log rank by lifting from query complexity. Essentially, I mean, that's kind of the, I shouldn't even say modern interpretation. You can even see it in their paper. So they start with a separation in query complexity of the deterministic decision tree complexity, actually, of the sensitivity of a Boolean function. They find an example where this is polynomially larger than this Fourier degree. Okay, it's something like 1.63. So sensitivity is polynomially larger than the degree of your Boolean function. And now using this theorem, you can lift this to communication complexity. You use this gadget, apply the theorem. That says that the deterministic communication complexity of f composed with this constant size gadget is lower bounded by the sensitivity. And on the other hand, here you can use this degree to rank lifting, although in the easy direction, the direction that says degree bounds give upper bounds on log rank. Okay, so this is a mere observation. It's not really lifting, it's the easy direction. So there you go. This is already useful to prove some applications. This was from 1994, and this was the best example we knew of until only a couple of years back. So now we actually have a separation that's quadratic, and it's proven, again, via lifting. It's really powerful stuff. So I think we should pause for the break. Are there any questions before?
I don't have a question, but I have an announcement.
Okay.